Okay, so let's do these two questions on Euclidean geometry. They are sort of two slightly more difficult questions that I found that I wanted to go through with you. In the first one, it says to us, in the diagram, triangle ABC and ACD are drawn. So you've got two triangles, ABC and ACD, and they tell us that F and G are points on sides AB and AC respectively, such that AF is 3x, FB is 2x, AG is 12y, GC is 8y, and HE and K are points on side ADK. And we've got two pairs of parallel lines. So we've got GH parallel to CK, sorry, C is kind of hidden down there. And we've got GE parallel to CD. So that makes it quite a little bit more difficult here because we've got two pairs of parallel lines. All right, so the first thing that they want us to do for 2 marks is they want us to prove that FG is parallel to BC. So we see FG down here. We see BC over there. Which triangle do you think they want us to work in? Exactly, they want us to work in ABC, all right? So how else can we prove that lines are parallel to one another, but we can't work with angles? We can't work with alternate angles that are equal or corresponding angles that are equal. We've got to use something else. So something from our matric syllabus.
Equiangular triangles.
But if we don't know anything about the angles velocity, then we can't prove equiangular triangles in this particular case. So this is a question. It's not the proportionality intercept theorem, it's the converse of the proportionality intercept theorem. Does that ring a bell? Converse proportionality intercept theorem? That ringing a bell? Converse proportionality intercept theorem? Okay, now we've also got to be careful about the way in which we set this out because we're proving that the lines are parallel. So what we would do here is we would say AF over FB is equal to 3x over 2x. Okay, so that would be equal to 3 over 2. Then we would state that AG over GC is equal to 12y over 8y. That would also be equal to 3 over 2. So if the two things are equal to the same, then they must be equal to one another. So that means that AF over FB is equal to AG over GC. Therefore, FG is parallel to BC, converse proportionality intercept theorem. Okay, and the way in which we set this out, guys, is very important. If we write this AF over FB equals AG over GC first, they're going to say, no, 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 no. Okay, that's what we're trying to prove. Okay, it can't be what the first thing that we write down on the page. It's our deduction. It's not our opening statement. Okay, so there would be 1 mark for getting that, and then a statement reason mark on AF over FB equals AG over GC, and then our reason converse proportionality intercept theorem. Okay. Now, in the second question, they want us to prove that AH over HK equals AE over ED. Okay, so let's keep that on the screen. So AH over HK is equal to AE over ED. How are we going to do that? Any ideas? If we want to prove that two things are equal to one another, we would, yes, iPhone, that's quite right. Triangle ACD is the correct triangle to work in. What is AH over HK equal to? What does AH over HK equal? Good. AG over? Over GC. Good. Well done. Reason? Why is AH over HK equal to AG over GC? Our reason? Proportionality. That's it, Chloe. Okay. Proportionality intercept theorem. And then remember, we've got to name the parallel lines. So we have got GH parallel to CK. All right. What does AE over ED equal? Staying in the same triangle, what does AE over ED equal, guys? Exactly. It's also AG over GC. Good. Well done. It's also AG over GC. And for the same reason, because of proportionality intercept theorem, except now we've got different parallel lines. Now it's because GE is parallel to CD. So what we notice is that AH over HK and AE over ED are both equal to AG over GC. So now we can deduce, therefore, they're equal to the same thing, then they have to be equal to each other. All right. That was out of, let me just see in the marks here, that was out of 3 marks. Okay. So they're not going to give us a mark on trying to think. So there must be a mark on that. There must be a mark on that. And maybe that they're both equal to the same thing. Okay, but they're not going to give us a mark on our final statement because that's what they asked us to prove. Everybody happy so far? Any questions? All good. Thanks, Avio. Okay, let's keep going then. Yes, okay, iPhone, cool beans. Thank you, Swanaka. Good stuff. Now, next thing, it is further given that AH equals 15. Okay, let's put that on the diagram. AH is 15. ED is 12. They want us to calculate the length of EK. Okay, so that's this little bit over there. Okay, so if it's further given, AH is 15, ED is 12, calculate the length of each K. Now, this is out of 5 marks, so we know that this is going to be a little bit more rigorous. Okay, where do you think we should start? What can we calculate the length of on that side. So on side AD, what could we calculate the length of? Based off of the information we already have, we can calculate the length of. Okay, we could calculate, it's not what I was thinking where we could start, but that's true. Yes, absolutely, we could start there. So Shisana says we can calculate the length of HK. All right, you're not wrong, Shisana. Absolutely, we can calculate the length of HK. How are we going to do that, Shisana? What are we going to sub into if we want to calculate the length of HK first? What would we write? What's AH over HK equal to? You already know from 4.1.2 that AH over HK is equal to AG over GC, right? That was the first thing that we wrote over here. So we know what AH is. We know that it's 15. So we've got this. We know what AG is. It's 12y. And we know that GC is equal to 8y. So that means that we can work out what HK is equal to. All right, so that's fine, Shisana. Let's start there. I like your suggestion. So this is question 4.1.3. So we know that, I'm just writing it all out for you again so you can see what I'm subbing into, is equal to AG over GC. We could say here proved above instead of having to write out the ratio again. We know that AH is 15, that's given. HK we can calculate. We know that AG is equal to 12y, and we know that GC is equal to 8y. So our y's are going to cancel out. We can cross multiply. That gives us 12HK is equal to 15 times 8. 15 times 8 is equal to 120. So that means, well, sorry guys, let me just try that again. So that means that HK would be equal to 10, right? Are we all good with that? That's it, Chloe. It is indeed. HK is equal to 10. All right, so thanks, Shisana and Chloe. We've now got that HK, this bit over here, is 10. We're getting ever closer. What else can we calculate the length of on that side? What else can we calculate the length of?
Ma'am, I found that HD is also equal to 10.
How did you get HD? Oh, you worked in... Really? And I don't think HD can be equal to 10 because EK is equal to 12. Okay, and also you don't, line GH is not parallel to line CD. So we can't make a proportion there. This is the tricky part, I think. Maybe working out HK was a little bit easier. Remember, just going back to our question, guys, they want us to calculate the length of EK. They want us to calculate this little blue bit over here. So if we know the length of HE, we can work out the length of EK by subtraction because EK is going to be equal to 10 minus HE, right? Does that make sense to everybody? So EK is going to be 10 HK minus HE. So how can we work out the length of HE? Let's just see what you guys come up with. Work out AD. Yes, we're working in triangle CDA. So here, what we would actually want to do, guys, is we want to work out the length of AE. We want to work out the length of AE because CG is parallel to CD. So that's a third side parallel. That's it, Letu. Work out the length of AE. If we get the length of AE, right, we can work out the length of HE by subtracting, because AE minus AH will give us HE. Do the rest of you see that now? It is indeed, Shisana, quite right. Good, Avayo. All right, so now let's work out the length of AE. Remember, AE over ED is equal to AG over GC. Right, we've got that over here, haven't we? So just like we used our previous question, now we can use this over here. All right, so let's put that down. So we've got AE over ED is equal to AG over GC. Again, it was proved above. And AE is our unknown. We know that ED is equal to 12 because that's given to us. And we know that HG over GC is 12y over 8y. Our y's will cancel. And now we can cross multiply. So that gives us 8AE is equal to 12 times 12, which is 144. So that means that AE will be equal to 18. Does that make sense to everybody? So we're just using what we've actually already established in question 4.1.2, and we're subbing in there. It is indeed, Shisana, well done. Okay, so now we know that AE is equal to 18. So that means that HE is equal to 3. Does that make sense to everybody? Okay, because HE is equal to AE minus AH. HE, so sorry, after this is part of our different question, sorry. Let's just keep that separate. So after this, I'm kind of coming up here so that I don't keep writing below all the time. So HE is AE minus AH. Is AE minus EH. So that is 18 minus 15, which gives us 3. And now we know that HK is 10. HE is 3. So the difference between them will be EK. So EK is HK minus HE. So that gives us 10 minus 3. So it will be equal to 7. That's it. Good. Well done, iPhone. Okay. Is everybody happy with that? 5 marks. So a lot going on in that diagram over there. Is that okay? Is that making sense? Sorry, I know it's always difficult when we're going up and down, and it's not all in front of us at the same time. Okay, so we would need to get HK as 10, right? We need to get AE as 18. we need to get a mark on our answer. We had to get that. So where else would they give us a mark here? Not sure where the 5th mark is going in this case. Maybe on that, I'm not sure. All right, are we all feeling good about question 4? We can move on to the next thing. Okay, here we go. Okay, so you can see here, this comes from a 2017 paper. And they're telling us in the diagram, LK is the diameter of the circle with center P. So the minute they tell us that a line is a diameter, what do we start thinking about? I would say angle in a semicircle would be the first thing that I would think of. That's it. And then they tell us that RNS is a tangent to the circle at N. So when we see the word tangent, there's 3 things we can think about. The first one would be tan chord theorem. The second one would be tangents from the same point, which would not be applicable here because we haven't got 2 tangents. Or we could have radius perpendicular to tangent, but we wouldn't have that here either because we don't have a radius touching at the point N. Okay, then what else do they tell us? T is a point on NK. All right, cool. And TP is perpendicular to KL. All right, fine. And PLN is equal to X. All right, now the first thing that they want us to do is prove that TPLN is a cyclic quad. It's out of 3. So it's not that rigorous. If it was really rigorous, it would be out of 5. So let's go and highlight TPLN. So that's this quad over here. Well, I think we've actually just done it, haven't we? Can you see I wrote down that N2 was equal to X. Sorry, talking nonsense. N2 is equal to 90 because of angle in a semicircle. So N2 and P would add up to 180 because they're both equal to 90. So therefore, the opposite angles of this quad are supplementary. So the quad has to be cyclic. Does that make sense to everybody? That's it, Mbalente. So we can see that. Is that cool? All right, lovely. So we're going to say that N2 is equal to 90, angle in a semicircle. And then we're going to say, no, not therefore. We're going to say P equals 90. So LPT, let's call it that. And that was given to us. So therefore, when we add N2 and LPT, we get 180. So therefore, the quad is cyclic. And our reason here is converse. Opposite angles of cyclic quad are supplementary. All right, so that was out of 3. Statement, reason, statement, reason. Yes, Penga. So I don't know what your teachers have taught you. There are other ways that you can say this, but for the years that I've been teaching, I've always used the word converse, because then the students don't have to learn 2 different things. So when you want to prove a quad is cyclic, it's converse angles in the same segment, converse opposite angles of a cyclic quad are supplementary, or converse exterior angle of a cyclic quad. Okay. Yeah, they are much easier to remember because, I mean, you've already learned the opposite angles of a cyclic quad are supplementary. So, you know, to put the word converse in front of that when you're trying to prove the quad is cyclic is just easier. Okay. Yolanda, would you be able to reach out to Shem? I don't know who it is. It's iPhone 2, and just help there. Because I want to move on to the next question. I think they're just struggling to understand 3.1.
Okay, perfect.
iPhone 2, not iPhone.
Okay.
Oh, okay. iPhone 2 says it's fine. It's fine. Are you sure?
Oh, okay, perfect.
Okay. Are you sure? Shem, I feel terrible calling these children iPhone and iPhone 2. What's your name? So we don't have to call you iPhone 2. What's your name? Please tell us.
Please, because if you can tell us, I can change it.
It's
Also
Chelsea.
on
It's
the chat.
Chelsea. There we go. It's Chelsea. Please change iPhone 2 to Chelsea. That's
Chelsea.
better, Chelsea. I'm calling you iPhone. Sorry, Chelsea. Are you sure you're okay, Chelsea? Okay, my girl, no problem. All right. So they then want us to determine with reasons the size of N1 in terms of X. Where's N1? Okay, so N1 is this angle over here. And they want it in terms of X. So they don't actually want its size, but we've now got to figure out what it is in terms of X. Okay, Avio, that's cool. Can you tell me why you're saying that, Avio? All right, so let's see what N1 would be equal to. So we know that N1 is the angle between a tangent and the chord. So it would be equal to an angle in the alternate segment. So we can see that it's equal to K. All right. What is K equal to in terms of X? Well, if we look at the triangle, so now we're looking at this triangle here because K is an angle in the big triangle. We know that this angle's 90. We know that that angle's X. So that means that K has to be equal to 90 minus X. So hence N1 is also equal to 90 minus X. It's okay, Avio, don't stress. Okay, N1 equals K. Yes, Chloe, it does. Okay, and K is 90 minus X. Good, Chloe, well done. All right, so let's get that down. So let's say that angle K is equal to 90 minus X. That would be angle sum and triangle because we've already proved that this is 90. We've been given that that is X. Therefore, N1 will also be equal to 90 minus X. And our reason there is tan chord theorem. Let's just check again. How much was that? Was out of it was out of 3. I'm sure that would be statement reason like so. Okay, so now we're starting to come to the slightly more interesting questions, right? These are our sort of typical grade 11 stuff, the kind of things they expect us to be able to do, even though they're not necessarily all that straightforward. And now we seriously are getting into the matric stuff. So the first thing that they want us to do is prove that these two triangles are congruent, similar to one another. And that's probably out of 3. Let's just check. Yes, it is. And again, if they tell us which triangles to work in, it just makes life so much easier because they're already telling us that the angle K in this triangle and angle K in that one are equal. They're telling us that angle T in this triangle and angle L in the other triangle are equal. And they're telling us that angle P and angle N are equal. So once we know which angles are equal, we've just got to go and look at them and try and find connections between them. So we start off by stating in triangle KTP and triangle KLN. All right, so point number 1. Let's highlight these triangles just to make them stick out. Let's just use a different color here. So we want, let's go with green, KTP. Okay, so here's KTP. In fact, what I'm going to do is I'm going to rub all of this off. And let's go, KTP is there. Right. And I think it's important that we know that this angle here was 90 minus x. Okay. And of course, if that's 90, this over here also has to be equal to 90 because they're adjacent angles on a straight line. And the other one was KLN. KLN. So that's the big triangle. Okay, so that. Okay, so this is not a particularly difficult. Okay, so K is common. Good. Good. Well done, Chloe. K is common. Excellent. So K is common. Awesome. Well done. Second reason, guys. We've already got it as well. Remember, so we could either work with that angle there and this angle here. Absolutely. Let's just do that. I think that would be the easiest. So let's call it TPK. So TPK is equal to 90 adjacent angles on a straight line, and angle LP, angle N2 is equal to 90. That was proved above, or if we want to, we could write again, angle in a semicircle. So therefore, angle TPK equals angle N2 because they both equal 90. All right, and then our last one is going to be angle T2 in the little green triangle, and it has to be equal to angle L. In the other triangle, angle sum in triangle, or remaining angles of triangle, okay, or sum of angles of triangle, absolutely. Okay, so therefore, triangle KTP is similar to triangle KLN, angle, angle, angle. Now, when they mark this question, I'm sure your teachers at school have told you this before. I'll just remind you as well. They can mark it in two ways. Either they will mark the first two, because remember, you're not allowed to use angle, sum, and triangle in either of your first two reasons, and then on the last line. Or the other way that they can choose to mark it is they can mark 1, 2, 3, like so. So it's either or. I don't know what they'll choose to do at the end of the year at marking, but it will be either one of those two scenarios. Just whatever you do, you cannot say angle, sum, and triangle as your first reason or your second reason. Okay, it has to be something else. It's only the third thing where you can say angle, sum, and triangle. Yes, Howard, go for it. You're welcome to unmute and speak.
Hi, ma'am.
Hi, Sahal. How are you?
I'm good, and you, ma'am?
I'm fine, thank you. What did you want to know?
Ma'am, I have a question about statement 3. Could the reason have been remainder angles?
Remaining angles, absolutely. Absolutely, not a
Okay,
problem. Yeah, not a problem at all. Okay, so you can use remaining angles in triangle or remaining angles if you want to. Okay, not a problem at all. And in fact, if you did angle, sum, and triangle, you'd see that T2 is also equal to X. Also, remember, you've proved that TPLN is a cyclic quad. So angle T2 is the exterior angle of the triangle. So you could say that T2 equals X, L equals X, they both equal X. You could also, we didn't do that, but that would also be acceptable. Yeah. Okay, Chloe, so that would be just a different way. We work with a 90, but yeah, if you want to work with T2 equals X, that would also be absolutely fine in this case as well. Okay, all right, so now on to the interesting question. And this, again, it's out of 5 marks. So it's like this one up here, it was out of 5. So we know that there is some rigor and some difficulty here because it's out of 5 marks. So it's going to stretch us a little bit. So now they want us to prove something rather interesting. They want us to prove that KT times KN is equal to 2KT squared minus 2TP squared. So when they want us to prove that two things are equal to one another, a strategy that is often helpful in a question like this is to separate the two from each other and ask yourself what they would be equal to. Furthermore, if you've got KT squared minus TP squared, where do you think that comes from? If sides are being squared, and hint, 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 we've got right angles here. It comes from Pythagoras, absolutely. So we're suspecting that there might be some theorem of Pythagoras coming into this. So it doesn't matter on which side we want to start. Maybe we can start on the right-hand side. If we've got KT squared minus TP squared, let's go and find KT and TP in the diagram. So, oh, I've lost my pen. Oh, there it is. Okay. So what I'm going to do, I was going to rub these sides out again, but I suppose I don't have to. KT, where's KT? Okay, so KT is this side over here. There's KT. And TP is that side over there. Okay, that side over there. So what would KT squared minus TP squared be equal to? Can anybody tell me? Good, Chelsea. Okay, it would be equal to PK squared. All right, so let's use that as our starting point. So in 3.3.2, let's start off with PK squared plus PT squared is equal to TK squared, okay, because of Pythagoras. So making PK the subject of the formula, PK squared, what am I writing, R? So PK squared is going to be equal to KT squared minus TP squared. So we've got part of this, both of them have been doubled. Okay, so in other words, I'll just put this in yellow. If I multiplied this by 2, it would be 2 PK squared would be equal to 2 KT squared minus 2 TP squared. Is everybody happy with that? I've just multiplied through by 2. So I've multiplied every term in the equation by 2. Is that cool? Does it make sense, everyone? Okay, just so that I can get what's here on the right-hand side. I just want to see what it's equal to. Yes? Yeah, because it's in the questions, Shisana. Does that make sense to you? It's just because it's in the question. You're happy with that? Okay, all right. So now I'm going to concentrate on the left-hand side. So now I want to look at this. Okay, and now somehow I have to relate 2 PK squared or PK squared has to be equal to KT times KN. That's what I need to prove. PK squared has got to be equal to KT times KN. So PK squared has got to be equal to KT. Sorry, guys. Didn't want the dot there. This is what I need to prove. I have to prove this. So I'm not going to write it down as though it's a statement, but this is what I've got to prove. So Trish is saying, can we use similar triangles? Okay, so if we did that, Trish, if we undid this, if we had PK at the top over here, we've got to have PK at the bottom to get PK squared. If I put KT over there and KN over there, I wonder if these triangles that we've proved are similar would come into this or not. Let's have a look. So let's go across the top. PKN is PKN a triangle? No, it's not. So across the top's not working. Let's go around the outside. Is PKT a triangle? Oh, yes, it is. Okay, so this worked, Trish. That worked around the outside. Is KNPK? KNPK. KNPK. No, that's not working. KNP, sorry, it's KNP. Is KNP a triangle? KNP is not a triangle. Okay, so now we've hit a little bit of a snag. Okay, now it's what I was saying to the other class this evening. Just because you've tried something and it doesn't work, let's try and think of something else. All right, so trying to prove triangles similar in this case was not a solution for us. So let's go back to the diagram and let's think about what else could work in this particular case. So I want you to look at the diagram. So KT is the side over here as well. And KN is the whole thing. Sure, Zwanaka. So I don't want to tell, well, I can't leave it too long, obviously, because it's almost 10:02. But I just wanted to give you guys an opportunity just to think a little bit. All right, Swanaka. Let me give you a little hint. Okay. PK equals LP. Why? Exactly, because they are radii. All right, good. So LP equals, let's just write that down. LP equals PK. Because they are radii. Just give you another chance to think a little bit more. That's anyone got any ideas? Are we stuck a little bit? It is tricky. It is tricky. You want me to do the rest of it? Okay, Shisana. Okay. What I'm going to do is I'm going to work at the big blue triangle, and I'm going to do the theorem of Pythagoras there as well. Okay, so I've got ln squared is going, sorry, not plus, ln squared plus kn squared is going to be equal to lk squared because of the theorem of Pythagoras. Then what I'm going to do now is I don't want kt, I want kt and I want kn. So how would can we use kp over kl? No, you know why you can't do that, Sihawu, sorry, is because PT is not parallel to LN. Sorry, Sihawu was just asking me a question if we could use proportionality intercept theorem. But no, that's not going to work in this case because you don't have a line drawn parallel to the third side of a triangle. Okay, so that's not going to work. Okay. So now what I want to do is in place of LK, I want to express LK in terms of PK. So what I was saying here about LP being equal to PK because of radii is what's important. So in place of LK squared, I'm going to write 2 PK squared. Does that make sense to everybody? So I've rewritten LK as 2 of PK. LK equals 2 of PK. Does that make sense to everyone? All right. So this is Kn squared plus Ln squared. Okay. Now we want Kt times Kn. Sorry, I thought this through earlier and then now like, what are we doing? Sorry, Matrix, just give me 1 second. Not 2pk squared, right, ln. I somehow feel that introducing this ln squared here, we need to get rid of that. Because that is not part of what we've got here. We've got the kt times kn Okay, you know what I'm going to do here, guys? Just give me 1 second. Hold on a second. What did we do here? Okay. Times KL. Okay, so we proved the triangle KTP and triangle KLN were similar to one another in question 3.1, right? So that gives us, hang on 1 second, okay, so when we proved that these triangles were similar to each other, sorry guys, what we can write here is that KT, so the first two over the first two over KL, is equal to TP over LN is equal to KP first and last over KN, because the corresponding sides are in proportion. So on the left-hand side, what do we want? We want KT and KN, right? So we want KT and KN. So let's work with these two. So that means that KT over KL is equal to KP over KN. If we now cross multiply those two, because we've got KT times KN, we cross multiply these two. KT times KN is equal to KL times KP. There we go. All right. Now, this is the bit that we need. Sorry, because that ln squared is actually not going to take us anywhere. This is the bit that we need. So when we come back up here, and we go and we look at our diagram, you can see that KT times KN is KL times KP. KL times KP. What is KL times KP over here? So you know that LK was equal to 2PK. So if I now go and sub in, so this was equal to KN, KT times KN. I'm now going to sub in place of LK. This is equal to 2PK times KP is equal to KT times KN. So this gives me 2PK squared is equal to KT times KN. And now I have two statements. This one over here, that 2PK is equal to, and this one over here, that 2PK squared is equal to. And now I can conclude that therefore KT times KN is going to be equal to 2KT squared minus 2TP squared.